saver, love is a doom, feathers on my breast. Gentle impulsion shakes me, makes me laugh, feathers on my breast. Teardrop on the fire, feathers on my
Ladies and gentlemen, it is a genuine privilege and honour to be here to deliver the John Orr lecture. I was aware of this lecture series years and years ago when the great Ron Ayres, who is not only the cleverest man I know, but also the oldest man I know, having been working in science and engineering since just after the Second World War, and having worked on aeroplanes and missiles when I was still was just being born. He has given this lecture series twice. I've listened with fascination to his stories about the South African hospitality and the prestigious nature of this lecture. So to be invited to give this is genuinely an honour. So thank you very much indeed. It's wonderful to be here. I don't really need to tell you what I'm going to talk about because you've just heard it. But I'm going to touch briefly on something I think John Orr would have appreciated, because he was not only a great engineer, he was a great engineering educator. He saw the need to put that education out there and to bring on the next generation of engineers. And that's exactly what Project Bloodhound's about. It is much, much more than simply another technical challenge for a motor racing organisation, albeit we're somewhat different, but I'll come to that later. So we'll talk about that, and I think John Orr would really have appreciated that, and he would really have understood it. So I think my job tonight is to try and explain to you how we're doing that, how it sits in the context of the history of the land speed record, which does involve South Africa, how and why we developed the technology with the thrust supersonic car, which we are now relying on to design and build Bloodhound, and how and why we're doing it in the first place. We already hold the record. I'm going to look at some of the technology of what we're developing right now and what we'll be doing in 18 months, 2 years' time in South Africa. And then a little bit, we'll look at the desert in South Africa and what it's, the state of it right now. And then finally, I'm going to finish up with an invitation to all of you. Firstly, though, I'd like to jump back to 1928. The great Malcolm Campbell, the most prolific record breaker in the history of the record, came to South Africa with a and I'll set myself a challenge here of trying to talk in kilometres. Bear in mind if I have to think about this. With a 350 kilometre an hour car. He was going to set a record of 350 kilometres an hour, and he had found the perfect desert out in the Northern Cape, a place called Finucane, with apologies for my pronunciation. The record then stood at 330 kilometres an hour. He had a 20 kilometre an hour margin. That was plenty. He was going to be able to set this record comfortably. At the end of 1928, he got out to Finucane and started preparing the longest prepared track in the world at the time. He was preparing a 25 kilometre long track to make sure he had a perfect run up to get the car up to speed. And by February of 1929, he was ready to run. Unfortunately for him, that's still the end of the rainy season up in the Northern Cape. The track wasn't dry yet, it wasn't quite ready. So he sat, he waited. By the middle of March 1929, the track is still damp. In the meantime, his great friend and rival, Henry Seagrave, has taken a more powerful car out to the United States, to Daytona Beach, done 2 test runs and then 2 record runs, and set a record of 370 kilometres an hour. Campbell is still in the Northern Cape with a 350 kilometre an hour car, feeling thoroughly disappointed, having put 6 months of work into the track. In April, he finally gets the chance to run. He sets a world 10 kilometre record. He sets a world 5-mile record, but he can't get anywhere close to the 1 mile, the flying mile time of 370 that's just been set. It is one of the very few occasions where he missed setting a record. So there's a little bit of unfinished business there. But nonetheless, he was still the most successful record breaker with 9 land speed records in his illustrious career. And that's in the context of 113 years of record breaking, spanning 65 different cars. From the very first car in 1898, powered by electricity, it was a battery-powered car, went to the blistering speed of 63 kilometres an hour, which was slightly slower than the cycling record of the time. But it made the point. There was a record there to be raced, and immediately the speed started going up. People saw the challenge, and the technology developed with incredible speed. In the early 1900s, the first steam car set a record, over 180 kilometres an hour, 3 kilometres a minute, in an upturned boat on bicycle wheels. An extraordinary piece of technology, only recently beaten. That held the outright steam record for a very, very long time. The record then jumped on to actually the car that stopped Campbell getting the record. The first car that did over 350 kilometres an hour out in Daytona. Piston engines now arrived. Suddenly we're up to 480 kilometres an hour with Malcolm Campbell's last record. And then subsequently the first gas turbine car. Malcolm Campbell's son Donald is setting a record in excess of 650 kilometres an hour. Then the first pure jet car in America, and America now starts to dominate the record. First pure jet car to do over 800 kilometres an hour, and then subsequently over 900 kilometres an hour, leaving the way open for another American to build a rocket car to exceed 1,000 kilometres an hour for the first time. Subsequently, Richard Noble built Britain's first jet car and took the record back at just over 1,000 kilometres an hour, but had a hunger for much, much more, to demonstrate the absolute limit of technology, to prove that the majority of people and the majority of professors of aerodynamics who were advising him were wrong, and that you could build a car to go faster than the speed of sound. And in 1997, his team, of which I was privileged to be a part, took the thrust supersonic car out to America and set what is now still the current world land speed record, 1,228 kilometres an hour. Vaughan, the 8 is important. More importantly, 1,220 kilometres an hour is the speed of sound. That was comfortably faster than the speed of sound both ways. Supersonic both ways for the first time in history. And tremendously exciting. Just to give you some idea of that car and what we had to do to keep it on the ground, we had to find a way of designing a car that would stay on the ground, despite the majority of professional advice saying it cannot be done. The forces are enormous. If you get the angle of that car ever so slightly wrong, it is 1 degree too much nose down, you will generate 10 tons of load and crush the suspension into the desert, which from my point of view as the driver is not a good thing. If you have the car 1 degree too much nose up, it will generate 10 tons of lift. The front end of the car will come off the ground. It will hit 40 times the force of gravity as it hits a supersonic airflow. The engines will tear out of the bottom of the car. All the bodywork will fall off. I will lose all further interest in the proceedings. So we had to get the aerodynamics exactly right. Now, a traditional way of doing that is to put the car in a wind tunnel. That was never going to work. And for those of you who have heard one of Ron Ayer's lectures before, I'm very briefly reprising an astonishing piece of aerodynamic research that Ron developed as a new research technique, because this was not going to solve our problem. You can build a supersonic wind tunnel and blow supersonic air over that model. What you cannot do is build a supersonic conveyor belt to make the ground move supersonic underneath it. And it's what happens underneath the car that is the mystery. We already know about supersonic airplanes. It's the ground that makes the difference. That's the bit we had to research. This was the 1990s. Ron, despite being 900 years old, still very much at the cutting edge of technology, turned to a new research capability called computational fluid dynamics, the ability to model in incredible detail the airflow around a shape like this, including underneath it. Now, it was a fairly immature technology in the early 90s, but nonetheless, it was the best we had. On the plus side, it gave us a phenomenal amount of detail about everything that's going on around that car, where the airflow is, where the loads are, so we can work out where the angles are and how to keep it stable at any speed. The downside is we're running this simulation on one of the biggest computers in the UK, the Cray C90. Fantastic help from Cray. They donated a huge amount of computer time to us. This is the same computer that they had sold to the Met Office to produce the weather forecasts. We are now designing a car with a computer that produces weather forecasts. Can you see why we'd be a little uncomfortable with trusting the results? So we had to find a way of validating those two. If we can't use a wind tunnel, Ron then turned the problem around and said, we can't actually pass air over the model. How about passing the model through the air and finding out what happens? So he built a scale model found a supersonic test track that normally tests high-speed weapons down in South Wales, where incidentally Campbell set his very first record. It's astonishing how history links up. And passed this car across a surface at supersonic speeds, packed with sensors. And rather than describe that, what I'm going to do is show you a brief clip of video of that research. So you can see the model, you can see the gap underneath it. It's a 1.6 kilometre long track, packed with high-speed sensors. 0 to 1,300 kilometres an hour in 0.8 of a second, which has two huge advantages. First of all, to quote my great friend Ron Ayres, it's one hell of a lot more fun than wind tunnel testing. More importantly, the sensors on top of that car and underneath the car show you at a variety of different speeds what the airflow is doing, where the shock waves are, and where the loads are by implication. We can actually measure all of that because we can measure the pressures and derive the loads. If they don't agree with the computer model, you have two different ways of modelling, you have no idea which one to trust. If they do agree across a whole range of speeds and a whole range of positions on the car, they must both be right. They validate each other. And they did agree with astonishing accuracy across the whole speed range. Ron had created a new research technique in order to design and build a safe supersonic car, which is exactly what we did. And we built a, thinking in meters, 17-metre long car. It weighed 10 tons. It had some approaching 100,000 horsepower in thrust, and it was designed to do what it said on the tin, the thrust supersonic car. We were going to take it 2 ways through the measured mile and set the first supersonic record. To give you a sense of what that's like and some of the challenges from the control point of view, we had the aerodynamics mostly sorted, but it was still an immature science. There were things we couldn't model, things that we only discovered when we started running the car. And you'll get a sense of a bit of this. This video is taken from a tail camera on the car. What you're actually looking at here is you're looking down the back end of the jet engines, and then that is the cockpit. So I'm sitting just in there, and you can see the line setting off into the distance there. The white line is about 20 kilometres long, and this video will take us to the other end of it in 3 minutes. We'll start off very, very slowly. You'll hear the jet engines wind up and the car accelerate very, very slowly because the intakes are very close to the ground, and I don't want to suck huge lumps of desert into the engines. They are ex-Phantom engines, they're SPAY engines, they're known to be very tough, they're known to have the ability to convert seagulls into extra thrust. But I don't want to damage them too much, so it's a very gentle acceleration up to about 100, 150 kilometres an hour. At that stage, we've got a good airflow into the engines. I can wind them up very quickly to maximum power, pour neat fuel, select what's called reheat, neat fuel into the exhaust. It's very fuel expensive. It takes about 15 litres of fuel per second to do that. But actually, remember this was the 90s, it was okay then, we hadn't invented the environment. And the car then starts accelerating at some 80 kilometers, no, it's about 50 kilometers an hour every second. So it'll go from 300 to 800 kilometers an hour in 10 seconds and keep going at that rate. As it approaches about 1,000 kilometers an hour, you'll lose the picture for 3 or 4 seconds. This was the last run the camera ever took because it literally the components were starting to fall off their legs. And sitting behind these two engines, I don't blame them. And then as the picture comes back up just over 1,000 kilometers an hour, you'll hear the shock waves start to form over the canopy. You'll actually hear that through my helmet and microphone while I'm commenting on the control. And the car takes a dive to the left. We had actually built an unstable car. We had no way of knowing that in the 90s. My job was to control it. Full lock is not rescuing the car, so I throttle back the power to actually change the airflow and change the load balance on the car to actually get the car coming back towards the right-hand side. The right-hand side as you look at it. As soon as it does, put back to the floor, full power, wind the lock back off again as I straighten the car back up, going at 1,200 kilometers an hour into the measured mile. The measured kilometer takes 2.9 seconds. At the other end of that, I throttle back. We now start losing 70 kilometers an hour every second. And you'll hear the warning tones go off as all the oil rushes to the front of the tanks and the engines struggle for oil pressure because they weren't designed to be treated like this. And then the car rolls down, parachutes, and it all slows down. Have a look.
75 aside. Left leading, which is a nice change. 80% nozzle closed. 80 miles an hour. Looking for mill. Mill power. 150 looking for min burner. Nice light together, slightly wriggly. 200 looking for max. Focus now, Mr. Dog. 715 coming up. 350. 450. 500. Start to yaw, bring it back. Getting it back. Over 600, got it. 650. 700. 720 into the measured mile. 725, holding it. Let's press. Into the measured mile. Stop it. Wait for stability. 600, here it comes. 550, 4.6 to go. 530. Shoot one. Good shoot. Both oils, no worries. Man, that was hard work. Coming down to 300, looking for the recovery crew, can't see them. Dust on the outside, recovery crew visual.
And I'll stop that there because below about 300 kilometres an hour it gets so slow you can get out and walk. So a couple of things come out of that. First of all, that we have a technology that can do this. We have an aerodynamic research technique which we know and understand, which we've developed and we can rely on. And second of all, that even the smallest imbalances can result in quite a lively ride, even at supersonic speeds. Never mind trying a 1600 kilometre an hour. So we've shown the problem as well as illustrating the solution. And that was the record we set. The one that the majority of experts we spoke to said couldn't be done, and if it did, we certainly weren't going to see any visible signs of it. And yet the picture says different. What's known as the Schlieren effect, where the shock waves are actually changing not only the pressure but the temperature in the air, and it's actually refracting the light through it, and you're seeing the shock waves. The most extraordinary picture. Even the photographer doesn't know how he took that. He's being very mysterious about, oh, I'm not telling you. No, you don't know, do you? So we hold the record still. Still the only supersonic record. So why are we getting back into land speed record breaking? Well, there are two reasons. There's a weak reason, first of all, which involves building this car to protect the record. A car to go to, well, actually we don't need to go to 1600, we just need to beat the opposition. There's quite a lot of opposition out there. There are at least 4 other teams. That car we were racing in '97 has been re-engineered and is attempting to do 1300 kilometres an hour next year. That car is a jet fighter with the wings cut off. They found it in a scrapyard and they put wheels on it. I'm being slightly flippant, but I'm probably right to be. It's got a few technical issues. But they've already run, they're generating a lot of interest in the race to the next record, and they're also aiming for about 1300 kilometres an hour. That car is half complete. Rocket powered, he's talking 1500 kilometres an hour plus. He actually wants to compete with us. That car's just been launched, and they're just setting about the design and build of it. Similar sort of speed, 1600 kilometres an hour. What a brilliant, about every 40 years, happened in the 1920s, happened in the 1960s, about every 40 years, a whole bunch of cars suddenly crop up together and there's a massive race for the land speed record. And it's happening again right now. It's a very exciting time for the record. But it's also a financially austere time where we're environmentally sensitive. Is that enough of a reason to build something as expensive and as powerful as Bloodhound? Possibly. I would argue maybe yes, but it would be a weak argument. Separate argument. While we were talking to various companies about how we'd go about designing this, and this was a few years ago, we talked to the British government as well about whether they'd like to get involved to showcase British engineering. One message kept coming through. All of them, government, the British engineering and the technology companies were all short of one thing, and it wasn't money, it was people. It was scientists, engineers, the expert innovators that are going to grow the next generation. We discovered that in the UK we have more people studying at university, studying psychology, than we do mechanical engineering. Actually, I'm here to say that we are never going to get to that high technology, low carbon world of the future without mechanical engineers and the other science disciplines and the other technical disciplines. Now, we'll feel okay about it because we can have loads of psychologists to talk to. But that's not really the point. We must do something about this. Where are we going to get these scientists and engineers? And to give you a different quote from last year, the country faces a severe and ongoing shortage of engineers and technicians. And I've actually jumped continents now because I'm quoting the African Academy about South Africa. The Department of Labour in South Africa estimates that over the last 3 years you have had a shortfall in training of 34,000 engineers and technicians. 34,000. And the majority of applicants for the mechanical engineering disciplines are aged around 40 years old, which doesn't make it sustainable. We're not getting the youth in, and we're not getting enough of them in. How do we capture their imagination? How do we capture kids, the PlayStation generation, who know everything about using an iPhone, a laptop, a PlayStation? How many of them can actually take it apart and fix it? None, they're not designed like that. How do we get them engaged in the technology that we are all becoming more dependent on? That is the aim of the project. What we want to do is excite these kids about the magic of science and engineering. Not make them scientists and engineers, just enable them to consider it with all the other careers. So they are genuinely excited by a single project that is going to cover so many disciplines and cover it in the open and get them involved in some of the practical sides. That's Formula One in schools, kids using CAD software and computational fluid dynamics packages to design their own model cars. And we have a Bloodhound class in that, which is massively popular because it's so much faster than all the other Formula One simulation cars. Formula One, by the way, for the purposes of this evening's discussion, are very small, slow cars that go around in circles. and, by the way, take my life much too seriously, but that's a separate issue. And we also need a project that is going to appeal to the whole gender range, girls as well as boys. We need to get past the primary teacher that when we launched this said, oh, this car thing's all very well, but what about the girls? Well, the reason girls aren't going to an engineering is because of her. So we have to go around her and use informal education outlets as well as the formal ways of doing things. So this is Project Bloodhound. Completely the opposite way up from the normal land speed record programs. First of all, it's a showcase for that inelegant word STEM, but it's an incredibly important concept to get kids excited about. Not to tell them they're going to be engineers, because then you start sounding like their parents and they'll run in the other direction. Just to offer them something they'll find interesting. An iconic project they can get involved in. And the way we're going to deliver that is by building and running the world's first 1,600 km/h car, Project Bloodhound. And there are some FIA rules for the land speed record. Formula One, small slow cars, round in circles. The rule book's about this thick, and they all look identical because the rules are so, they have to paint them different colours to tell them apart. Land speed record, if you write them in really big letters, it goes about this far down the page. You've got to have 4 wheels or more. It's got to be self-powered, it's got to be wholly and continuously controlled by a driver, and do 2 runs through the timing lights in opposite directions within 1 hour, full stop. Innovation writ large. It's a blank sheet of paper to science and technology. It's a blank sheet of paper to the imagination. It's a blank sheet of paper to every school kid. You say, all right, how are you going to build a fast car? What are you going to need to consider? We'll talk about a few of those things. Because with the FIA rules, we don't have any competition. All the cars are different. All those other cars I showed you, completely different. So we can share everything. We have published all of our design drawings on the internet already, along with a freeware CAD package. They can download them and unpick them, disassemble the car on the computer screen. All the vehicle technical specifications are published on our website. Bits of the design software are published on our website. We can share all of it with a global audience. And it's not just kids up to 16, it's kids of all ages. I find this exciting. 6 to 96 is our target audience. That's what we're going to build. To give you an idea of what it's going to look like, how it's going to work, let me show you what a jet and rocket powered car looks like running on Haxkey and Pan in 2 years' time.
Bloodhound SOC, you're cleared. Engine start.
Bloodhound engine start. Ready to roll.
There you go, it's as easy as that. Informal education, reaching round that primary school teacher says, oh, cars are not for girls. The reason we produce these is we put them directly on YouTube. So far we've had 4 million hits on YouTube with this animation and another couple. We are reaching a big audience already. The Bloodhound effect, the equivalent of that Apollo effect, is already happening. Kids are already looking at that. How does that work? What makes it? And we can start to talk about a 13-metre long car weighing 7 tonnes, generating 210 kilonewtons, 130,000 horsepower, 180 small slow cows going around in circles. In fact, 181, but I'll come back to that. A car that will be 16 kilometres away in 100 seconds, and a car that will be running in South Africa in 18 months' time. A car that's using technology I've already talked about. We already know that this works. We're using the same techniques. We're actually using the same team. The guy who did the modelling last time was a young graduate called Ube Hassan. Professor Hassan's department is now working underneath him to complete this modelling. And it's actually great to have them involved. They are the world's leading experts in this and developing the code and these results. And that's exactly what they're doing for us. So I can stand here with confidence and say, these pictures say the car will stay on the ground and it will do 1,600 kilometres an hour. We know that because the first thing we did to validate this model was recreate all of the data from Thrust SSC in the modelling, which is why we know that we made some design errors and actually designed some instability in it. Because 15 years ago, that modelling didn't exist. We recreated all the data and learned a lot from it. We know this is going to work. We will still spend a long time up in the Northern Cape testing it step by step to validate it. It's still unvalidated, but we have a great deal of confidence that this is going to deliver what we need. It is, of course, going to take a huge amount of power to take a car to 1,600 kilometres an hour, where the drag alone is going to be 17 tonnes on the car. Combination of jet and rocket, it's a unique combination. It's quite a complex combination to make work. We actually need 3 engines to make this work in total. The jet engine, people's governments, it's from the Eurofighter Typhoon. They've spent an awful lot of money developing an engine which weighs 1 tonne, is 4 metres long, and develops 9 tonnes of thrust. That will get us up to about Mach 1, about 1,200 kilometres an hour. It will not get us anywhere near 1,600. We need a rocket motor in addition. But rocket motors are very expensive to develop, very expensive to run, and they are very difficult to control. So we have a cheap, controllable jet engine, and then effectively the booster rocket for the higher speed runs when we've done 90% of the chassis development, the car development, the aerodynamic development. And that is why Ron Ayres specified the combination. The reason for the combination gives us all the flexibility and the ability to do a lot of cheap runs on the jet without worrying about developing the power plant, so we can develop the car and the rocket in parallel. The jets themselves, we would never have got hold of a Eurofighter engine. They cost, thinking in rand, 50 million rand per engine. And the waiting list is years long. There are only 4 customers, and they are the military of the 4 Eurofighter nations. We were never going to get one. Fortunately for us, 5 years ago, when we went to approach the government and said, how about lending us an engine, the test program for the Eurofighter was finishing, and the development engines were being grounded. They are museum pieces. Still got some hours left on them. All the orange wiring, you can actually see that's test harness wiring. That's a development engine. That's effectively an EJ200 museum piece. So we're just recycling it. This is land speed record recycling. That's our 9 tonnes of thrust. In addition, we are also building our own rocket motor. Half the size, 12 tonnes of thrust for 20 seconds. It's a hybrid rocket. To make it safe, we have to have a liquid component so we can switch it off at any stage of the proceedings. So we have a solid fuel. The actual core of the rocket is cast with a solid fuel called hydroxyl terminated polybutadiene. There will be a test later. But actually, everybody knows what that is. HTPB is chemically aircraft tyre rubber. Near enough. Hold a match against it, it won't burn. Doesn't explode. It's a non-explosive rocket fuel. It's perfect. It's the safest rocket fuel you can get. Heat it up to 600 centigrade in pure oxygen, and it burns like that. So now we just need a safe way of generating very hot oxygen. High test peroxide, very, very concentrated hydrogen peroxide. Forced through a catalyst pack. Hydrogen peroxide is water with an extra oxygen atom, H2O2. You split it through a catalyst, becomes H2O, and hot oxygen releases a huge amount of heat. You finish up with oxygen at 600 centigrade. And it will then actually react and produce 12 tonnes of thrust, forcing its way out of the back of the rocket. That then produces an equal and opposite reaction, pushing the car forward with 12 tonnes of thrust. I'm about to show you one of our rocket tests. This is a half-power rocket test. And you're going to hear initially the sound of the oxidizer, the HTP, being forced through the catalyst pack. You'll see very quickly a huge cloud of steam. As the cat pack starts to heat up, the HTP breaks down into steam and oxygen. It then goes clear because you can't actually see steam. You can see the water vapor as it condenses. As it goes superheated, it stops condensing. It's too hot. So it actually goes completely clear. You then start to see smoke coming out the back as it starts to char the rubber. And as the rubber catches, then you will finish up with a flame like that. And that, going back to the animation, is everything that I initiate with the left-hand trigger there. That's effectively lighting the rocket up. And then full power is the right-hand trigger to get the full power going. Just have a look. If you're going to have a 1,000-mile-an-hour car, you've got to have one of these on board. Right, why have I just been into so much detail about how a hybrid rocket works? We've just covered a fair chunk of chemistry, a bit of thermodynamics. We've also looked at a little bit of materials properties and some Newtonian physics. What makes the car go is Newton's third law. Every action has an equal and opposite reaction. I don't know about you, I don't remember science lessons at school being that interesting. As the teacher going, here is a bit of what makes the car go, now let's talk about science lesson, pull whichever one you want out of the drawer. That's how our education program is working. That is what Project Bloodhound is aiming to deliver through a project like this. I mentioned the environment as well. Environmentally, burning that much rubber, irresponsible. We looked at the carbon footprint of the car. Go into the website, check my figures. If you disagree, please let me know. Assuming a 3-year total running life from first run to final record for the car, we worked out how many runs, how much fuel we would use, how much of the rocket fuel we would use, and the total carbon footprint of the car is about 50 tonnes of carbon dioxide. To give you some idea, spread over 3 years, that's the same carbon dioxide output as 4 dairy cows. So we could become carbon neutral just with one huge braai. Or slightly less flippantly, that is a very small investment in the future of science and technology and engineering and maths for a generation. That's what we're trying to achieve. That's why we think it's worth the investment. One of the disadvantages with using a complex hybrid rocket is you've got to pump the oxidizer. That pump is about this size, it's just bigger than a football, spins at 10,000 revolutions a minute, pumps 20 litres a second at 76 bar, 1,000 pounds per square inch, through the catalyst pack. Takes 700 horsepower to turn that pump. So just to drive the pump, we have last year's Cosworth Formula 1 engine. So add to small and slow, underpowered. And as I said, we're actually the power of 181 Formula 1 cars because one of them is a pump motor. But Cosworth also brings something magic, because Cosworth and Pi Research are experts in systems and systems integration. The complexity of this car is something we can guarantee will work because our systems engineer works in an office in Cosworth. That's what they do for a day job. They've put their name on the side of their car. They are going to make this work. So de-risking the project as an from an engineering point of view, taking the risk of all the complexity and getting a technical partner on board removes all of that risk in one go. One of the other bits of technical risk we had is the wheels. The wheels spin. They're about a 90 centimetre disc. They spin at 10,000 revolutions a minute. The wheel rims experience 50,000 times the force of gravity. That's near the limiting strength of most materials. You can use very exotic materials like titanium, but they're very expensive, they're very difficult to work, and they're not damage tolerant. We'd prefer to use something cheap, because we haven't got much money, but also something damage tolerant and proven. Aluminium is what we used last time, so we looked at designing an aluminium wheel. Lockheed Martin aren't a car firm. They are an aerospace firm, and these are aerospace numbers, aerospace spin speeds. And they've put something like 1,000 hours into designing out the problem that when you actually start to load up this sort of shape of wheel, you can see some orange hot spots up there, which is getting close to the limiting strength of aluminium. We needed a different shape, and they eventually came up with our wheel shape, which we are now putting into production and going to spin test for the first time. Those wheels will take comfortably well over 10,000 revolutions a minute. I am pleased to say, because I'm going to be between them when they're doing it. But another huge technical challenge and another piece of science and technology which is easy to explain, and we can share all the data, including the very sophisticated design and assessment techniques that Lockheed Martin used to develop them, as well as the whole construction of the car. The front of the car is going to be subjected to huge aerodynamic loads, 13 tons per square metre of aerodynamic load. Very complex shape. So, and it's taking the loads of the front suspension. Obvious choice for carbon fibre, complex shape, high loads. The back end of the car is much simpler shape. It's going to experience very high vibration, very high temperatures. Much more obvious, and you need to take it apart to get to the various engines and systems back there. So much more obvious choice for a steel space frame with metal panelling, which will take the heat and take the vibration much better. And suddenly, the materials start to select themselves, and your materials technology lesson is involved in the various different characteristics of the materials we've chosen and why we put titanium at the back and aluminium in the middle. All of that's now in construction. Hampson Aerospace, the world's largest tooling manufacturer, is making the back half of the car in steel, and the front half by the Advanced Composites Group, who make things like America's Cup yachts and small slow cars that go around in circles, and the wing spars of the Airbus A380. I've got a lot of confidence the Airbus isn't going to fall out of the air, a lot of confidence that their showpiece for next year is also going to work really well. And by the end of next year, we're going to have a car and we're going to start shaking it down in the UK. And as soon as we run out of room in the UK or run out of tyre speed to run on a runway, which will be about 250 kilometres an hour, I suspect. We haven't chosen the tyre yet, we're working on it. We're going to need to bring it to a desert and start going faster. The traditional solution is to go out to the US. This is where we ran last time. It's the Black Rock Desert in northern Nevada. That is actually the Black Rock at the end of the desert, after which it's named. That's what it looked like in 1997 when we ran there. That's what it looked like 3 years ago. It's been massively used since then, and they are having an ongoing dry period in the northern US. The reason these dry lakes form is they flood during the wet season, and then they dry out in the summer. 50,000 Americans go out, drive all over the desert, and then it doesn't flood in the winter. That's what happens. The surface just isn't recovering. We have to find somewhere else. So we went back to our favourite university, Swansea, and said, we've got another great opportunity for you. Be very careful if the land speed record team ever comes up to you with an opportunity. It's going to involve no money and a lot of work. Where in the world can we find somewhere else to run the car? We want to know all the deserts so we can actually rank them and then choose the best ones, or the best one. And they said, okay, the easy bit is where are you going to have to look? One of those 7 red boxes, any desert in the world is going to be in one of them. Yeah, that's not the hard bit. The hard bit now is actually finding all the flat surfaces. Let's take Australia as an example, because it's quite a good case study. In the year 2000, the Space Shuttle did a radar map of the whole globe. And the various environmental sciences departments can get access to this sort of stuff. So they download the model, build a computer program to search it, and start looking for square kilometres with very low variance. In other words, very, very flat. So we can now find flat areas anywhere in the world. Australia, for instance. The Landsat series take multispectral pictures regularly of the planet. 7 different frequencies. By choosing the combination of frequencies, you can look for different things. You can look, for instance, for vegetation. Or by inverting that, you can look for places where there's no vegetation. Flat and no vegetation are starting to sound good now. You can also look for water. Or by inverting it, look for lack of water. What we actually need, or you can actually look for shallow water, because the spectrum of very shallow water is a very light blue colour seen from space, and it gets darker as it gets deeper. So you actually look for no water or very shallow, because bear in mind the ideal surface might flood during the winter. So we're looking for very shallow water or none, no vegetation, and flat, square kilometre, and then the program looks for at least 15 to 20 kilometre blocks in the same place, and then it says Australia has that many, which is rather a lot. There is actually a fantastic desert here. Unfortunately, it's about 200 kilometres from the nearest gravel track. Not road, gravel track. It's a long way from nowhere. So the physical challenge of getting out there, it's also relatively low level, so the air is very thick, it's not ideal. If there was nowhere else we could look at it. We didn't, because we looked at a whole range of other places. Didn't go to all of these places, but we went to a fair number of them. Some of them deselect themselves. The Rann of Kutch is on the India-Pakistan border. It's a disputed border. They have a war there every 10 years, whether they need one there or not. But there are a lot of other places, some we knew about, some we didn't, which we need to look at. Once we'd actually got them down to a sensibly short list of practical places that we could also get to, that we weren't going to get shot at, and that weren't flooded all the time, I then went to visit all of them, went across 4 continents, and I finished up in South Africa, where Malcolm Campbell ran in 1929 at Phnuc Pan. Fantastic pan. He got a 25-kilometre track. I only needed 20. We found somewhere that we could get 20 kilometres. The underlying surface is incredibly smooth and hard, the best I'd seen anywhere in the world. A lot of stones on the surface. It was going to be a huge effort to clear. It was also quite difficult to get to. Life support was going to be difficult. We could deal with those things. The main thing was clearing the track to produce the ideal track. We went to the Northern Cape and said, can we use Phnuc Pan and will you help us? And they said yes, which is an incredible thing. You know, some random individual walks through the door, says, I'm going to build a 1,600 kilometre an hour car, and would you like to spend an enormous amount of money clearing a desert just in case I turn up with one? And they said yes, which is a huge leap of faith. You know, and I am personally, the story I'm going to tell you now, I'm personally enormously grateful to South Africa and to the Northern Cape government in particular for showing that much faith in us that early on. And they did an initial survey to find out how much work was there, and they discovered something we didn't know. The piles of stones sitting on the surface, which have been washed down over millennia onto the surface, don't just sit on the surface. Actually, underneath this fantastic clay pan sits a layer of shale, and the shale in places has broken up. It's come together, and it's actually erupted and come up through the surface. So some of these piles of stones go all the way down. They're actually funnels coming up from underneath. So to clear a wide track for a jet car, I mean, Campbell took 6 months just to clear 30-metre wide strip for his car. We need a 1,500-metre wide strip for ours. It was going to take an enormous amount of work, and technically, to dig huge chunks of the desert out, to bring a huge lot of fresh clay in, to lay it, and then try and get it to be perfectly flat, that was a huge technical risk. What if it didn't work? What if it didn't rain properly? We could finish up destroying the desert surface. There was one other place in South Africa that was long enough, which had the same quality of surface. We went to have a look. It had a causeway running across it. They had just built a brand new tarmac road right next to the desert to get to Rietfontein, to get across to the border. So suddenly we could remove the causeway and make the whole 20 kilometres available. The track had just become available. A lot of stones on the surface, but they all sat on the surface. This was the solution. So at the last minute, and I'm kidding you not, the week before the press launch, the formal press launch of we're going to South Africa and we're going to run at, no we're not, we're going to run at Hackskin Pan. We changed with a week to go, and the Northern Cape since then have hooked into clearing the pan. This is going to be one of our first world records, the largest single area on the planet cleared by hand. And you have to clear it by hand or you tear the surface up. To give you some idea, they are clearing 25 million square metres. That is the same as starting from here with a team of people and clearing by hand all the lanes of motorway from here to Cape Town. It is the most enormous task. They've had 300 people out there all the way through this winter, clearing, because the winter's the dry season there. 300 people clearing that, and they will finish the job next year. We are going to turn up with the world's fastest car onto the world's best racetrack in South Africa, and the eyes of the world are going to be here. This is going to be the biggest engineering event in South Africa. Actually, it's going to be the biggest one in the world, and it's going to have the biggest audience. We're going to be sharing it with a huge global audience. We're going to be running live video from the car, because now the technology exists to put a video camera in the car and actually put it directly onto the internet, live. I was at a meeting this morning talking about how we're actually going to bounce that signal by microwave down to Uppington, put it into the fibre, share it with the whole world. The whole world is going to be able to watch that happening. Via the internet, via their mobile phones, whatever. The eyes of the world are going to be right here on the most remarkable car in the world. But actually, it's more than that. It's the most remarkable engineering adventure in the world, because we're launching not only the video, all of the data from the car we're putting onto the internet. So the kids can watch the car run and do their own data analysis, do their own assessment in parallel with us. While we're turning the car around in the desert for another run, they can do the same thing, and we're providing freeware on the internet to do that. This is the culmination of all those lessons on what makes the rocket go and why did you choose these materials for the wheels, is to actually study all of that. And that then remains there for the next generation in terms of getting the kids hooked on science and technology. It's not the you are to be an engineer, here's what to study. It's the have a look at this, see if you find it interesting. If they do, they'll make that decision for themselves. This is the very first run that touched Mach 1. It's just after a huge dust storm, everything's covered in dust, and the sun is very low, so it's some unique conditions. It's the only time these photos were ever taken. That's the car doing about 300 kilometres an hour. Approaching 1,000 kilometres an hour, the shock waves start to form. And you start, because the shock wave is a pressure change, it's lifting the dust just off the surface and it's glowing in the last rays of the sunshine. And as we approach 1,200 kilometers an hour, we generate a shock wave over 100 meters across. The other reason these pictures will never be taken again is because they were taken from a microlight, an ultralight aircraft. We had 2 of them airborne who were checking the desert was clear. One of them was a very good photographer. 3 seconds later, the car goes past and the shock wave arrives. Microlights don't go supersonic. And all I can tell you, ladies and gentlemen, is that Bloodhound is going to be different. I can't tell you how, because it's an engineering adventure and we don't know where the final destination is or exactly what the journey is going to look like. What I can tell you is we're going to share every step of that journey all the way to the final destination with a global audience, with a South African audience, with an education audience. And that is the aim of Project Bloodhound. And now, the invitation to all of you. I will close the John Orr Lecture 2011 with an invitation, not just to follow it, but actually more importantly, if you do one thing after this, consider signing up your local school. Get your kids, get next door's kids studying this. It's as simple as getting onto that website, registering your school, and then we will get in touch with you. We have a global network so far of 4,700 schools, mostly concentrated in the UK. We have 80 at the moment in South Africa. I want that to read in the thousands by the time we actually get here, because that is going to be of benefit to South Africa, and it's free to sign up. We now have a permanent education presence in South Africa, so you can also get involved as a volunteer ambassador. We will give you the tools and the presentations to be able to go out and talk about this science and technology in schools. Pique their interest. How does that work? Why have you done this? What's that about? You know, can I hear more about this? And that's all you need to do, and they're off and running. And we'll take it from there and share the adventure over the next 2 or 3 years. The fin is covered in thousands of tiny names, and for just over 100 rand, put your name on the fin, it'll be there forever, and we'll take it to 1,600 kilometers an hour one day, and your kids can go out and see it in a museum one day. Ladies and gentlemen, that's my invitation. I hope you enjoyed listening to the story. I hope you enjoy sharing with the adventure. It's been a great, great privilege to present the John Orr Lecture to you tonight. Thank you.
Let the race begin.